Okay, guys, we're going to discuss real gases and then go through the van der Waals equation. First off, real molecules do take up space and they do interact with each other, especially polar molecules. So we talked about the assumptions of the kinetic molecular theory. Real gases, they fit into the assumptions of the kinetic molecular theory, but there are some other things that we need to take into consideration. So the ideal gas law is good for estimating the behavior of gases under certain conditions, but in reality, gases do not always conform to all of those assumptions. So we have another equation that's going to account for this for us. So we need to add some correction factors to the ideal gas law to account for these differences or variations. So there's our volume correction. The actual volume, gases are free to move and is less because of particle size. So we assume that particles take up space and these particles actually have less area to move around in than what we originally calculate for in the ideal gas law equation. The greater the number of molecules, the greater the effect that we for this volume correction. Now we're going to show how this equation is derived, but in the end, I'm going to show you the actual equation. So B, it's a constant that differs for each gas, and that has to be given to you when we look at this equation. And the van der Waals equation is also in your gas law under the gases section of your formula sheet, so you can refer to that also. So we're starting to derive the equation here. Now, pressure also has to be corrected for. So we not only have a volume correction, but we have a pressure correction. Because molecules are actually attracted to each other, the pressure on the container is going to be less than what it would be under ideal conditions. And this depends on the number of molecules per liter. So since two molecules will interact, the effect must be squared. So that's how that affects this equation. So that is what A stands for. So altogether, we have this giant equation coming together. It's called the van der Waals equation. And I'm going to rewrite this for you. This is pretty good right here, but I'm going to rewrite this when we actually do the problem together so that you can see what everything stands for. So that's the corrected pressure, that's the corrected volume. Notice how it's incorporated into the ideal gas law. So A and B are both determined by experiment. Those are variables that have to be given to you on your take-home test. You see that I gave you variables A and B. It's different for every gas, so again, have to always be given to you. So the larger the molecules, the larger the value of B. And A depends on both size and polarity. So once you're given, you have to rearrange to solve for the variables. It's a giant algebra problem is essentially what it is. So here's our example. You're going to calculate the pressure exerted by 0.5 moles of chlorine in a 1 liter container at 25 degrees Celsius using the ideal gas law. And then we're going to use the van der Waals equation, and they gave us A and B. So first, let's do the ideal gas law. I'm going to switch over here to, you can refer to your notes, but I'm going to switch over so we can do this example on a different slide. Okay, so first using the ideal gas law, given the data that they just gave us, given that information, we can see that we're solving for pressure because it says calculate the pressure exerted by 0.5 moles of chlorine in a 1 liter container at 25 degrees Celsius. So pressure is our variable, and then 1 liter is our volume, 0.5 is our number of moles, our R value is 0.0821, and our temperature is 298 Kelvin. So when we solve for P using the ideal gas law for this problem, we see that the pressure is 12.2 atm. So this is a good estimate of the amount of pressure that these gases are exerting in this container. But in all actuality, gases are not behaving under ideal conditions. So let's account for the fact that chlorine does have intermolecular attractions, and chlorine does have a mass, and it does there's a quantity that takes up a certain volume. They gave us that the A and B constants back on the slide, so you can refer to that. Now I'm going to go ahead and rearrange van der Waals equation to solve for P. Here is the actual formula for van der Waals equation. So it's P plus n squared over A over V squared. Again, this is on your formula sheet. V minus NB. So the only two variables that are new here are A and B, and those variables have to be given to you, equals nRT. They gave us A is 6.49, and they gave us that B is 0.0562. So this is on your slide on page 9, the last equation. Now, they're asking us to solve for pressure here, so I need to rearrange this van der Waals equation to solve for pressure. So when I do that, I get P equals nRT over V minus NB minus n squared A over V squared. So that's just simply rearranging that equation to solve for P, moving the variables around. If you have questions on that, you can ask. So P equals, I'm going to start plugging the variables in. N still stands for number of moles, so there are 0.5 moles. R is still our gas law constant, 0.0821. T is still our temperature, 298 Kelvin. Over our volume was 1 liter, so 1, minus N again, which is 0.5. And then B, which is the variable that they gave us, is 0.0562. So this isn't really difficult. It's just a lot of numbers, a lot of substituting, and a lot of algebra. And then again, N is 0.5, and we're going to square that. And then B, or A, is the other variable they gave us, is 6.49. Again, has to be given to you. And then our volume is 1, and we are going to square that. So I plugged everything in to this equation. Now it's just a matter of solving for P. When we simplify and we solve for P, you should get 10.9 ATM. So notice the difference between the two. We have 10.9 ATM versus what we solved for with the ideal gas law, which is 12.2 ATM. So there is a difference, and intermolecular attractions do make a difference on the amount of force or pressure that molecules are exerting on a container. So 12.2 ATM versus 10.9 ATM. That's what the van der Waals equation does, is allow you to see how a real gas is behaving under different conditions. You cannot use the van der Waals equations if A and B aren't given. So normally you would just calculate this using the ideal gas law. This could be a problem on the AP Chem exam, though, where they would ask you to first solve the ideal gas law and then solve the van der Waals like we just did, and then compare the two and account for the differences.